Everybody, in this video we're going to be discussing matrices again, but specifically the elementary row operations that we typically perform on a matrix, okay, and the convenience of using a matrix as opposed to using a system, okay. So let's go ahead and get started. I've written a system over here on the left, okay, but you notice we have three equations and three variables. Let's go ahead and write an augmented matrix for this system, okay. So remember, go ahead and get started by including our square brackets. And so this is going to be -1, okay, 3, and we don't have a z term in our first equation, so we'll fill this in with a 0. 1 here, -2 and 3 for this equation's coefficients, and then we have 2, -5, and 5, okay. So far this is a coefficient matrix, okay. We're going to drop in our bar here and augment it, or modify it, and drop in our constants from the right side, okay. So we have our augmented matrix, which, by the way, it's good habit, I think, to write this down here. We have a 3 by 4 matrix. Okay, so this 3 by 4 matrix. We even call this matrix A if we wanted to. But in this video, hey, we wanted to discuss elementary row operations. So let's go ahead and visit these. And those elementary row operations, or EROs, we refer to them as EROs sometimes, are these. We are allowed to swap any rows that we want out. So all that means is we can change the order of rows, okay? We never do that with columns, really, with linear systems, at least not in my experience. You may do it other times, but you can swap rows, okay? We can also scale rows, and by scale rows, what I mean is you can take an entire row times a scalar, and it's still what we call a row equivalent matrix. It's the same system, okay? And it's just like when you eliminate with systems, you can multiply or scale an entire row, and it doesn't change the solution to the system, okay, or solutions. And last but not least, we may add a scalar multiple of one row to another row. Okay, so in other words, we can scale a row and then toss it on to another row, and in hopes of eliminating things, just as we would if we were dealing with a system. Okay, and so the nice thing about it in this video, as we use these EROs, you'll start to see why matrices. Why would I rather use a matrix as opposed to the system? And really, it's so we can kind of streamline things a little bit here. You just get used to looking at coefficients as opposed to, you know, variable names, which kind of are just eye litter, you know. I mean, it's in the way. So starting with number 1 here. So I said we could swap rows. Now I have to let you into a little bit of my thinking here. What we're going to be attempting to do here is you see this main diagonal here. And so that would be these terms here. So we've got A11, A22 if we wanted to name these, A33, and this is not a square matrix, but what I'm going to attempt to do is I want to alter all these into being ones, okay, and positive 1. And we'll talk about the value of this once we get to that form. But what we're going to do is we're going to refer to that as row echelon form. Okay, so row echelon form is our goal. And we might as well kind of go ahead and define this slightly. But row echelon form has a couple of stipulations. One is any, all, 0, 0, 0 rows to the bottom. We don't want to deal with them up top, okay? And then another stipulation is this. Any rows, let's just say this, all, let's go back. Let's say this, all non-zero rows. Okay, so all non-zero rows start with the leading one. Leading 1. Okay, the digit 1. And so check this out. I mean, like, I guess what I'm saying is if we had a 0, all 0 row, we'd put it at the bottom of this matrix because, hey, we can swap 2 rows. That is totally fair. But also this, we want all these down our leading diagonal here to be 1s, okay? And so since they're all non-zero rows, we'd say I have a leading 1. Now I also want you to notice that if these were 1s, these pink boxes here, then what I could tell you is, and they'd have to be leading 1s. I mean, like nothing in front of them could be anything but 0. I want them to be the first numbers in the row. But you notice they're kind of in this diagonal form. And that's what we kind of want. And so I could write number 3 up here. But essentially, any row with a leading 1, okay, if you go the row above it, so here, we'd say that leading 1 right there would be to the left of this leading 1 right here would be to the left of this leading 1 right here. Okay, so let's go ahead and get started with our ERO edge here, and I'm gonna get rid of some of this mess. Okay, so we said we could swap two rows. Let's go ahead and do that. I want you to see how you would write your work here. I'm interested because I want to have a leading 1 in this top corner here first thing, okay? And getting a leading 1 up there that's positive, I noticed that there's already a 1 right there that's positive. So what I'm going to do is I'm going to switch my two rows. So I'm going to make row 2 row 1 now. So I got this, and then our 9, and then we've also got so row 1 became row 2, -1, 3, 0, -4, and then 2, -5, +5, and 17. Okay, and so we have this new matrix, and to show our work, what we'll just do is this. We'll say, okay, so row 1, interchange with row 2, and simply put, that's what we've got here. Okay, so now what I'd like to do is get all of these, okay, because I just want my 1 here to be isolated in this column. I want to get anything underneath this 1 to be equal to 0. And so what I'm going to do is I'm actually going to add row 1 onto row 2, because what I notice is this leading 1 here, if we were to add all these coefficients to these coefficients here, then it would cause this to cancel out. Okay, so what we're going to do is we're going to say, all right, negative row 1, sorry, not negative row 1, but row 1 plus row 2. That's what we're interested in doing here. So we're going to write down our operation. We say row 1 plus row 2. Now the important thing to note here is when we add or scale and add a row onto another one, that individual row itself doesn't change. The only row that changes is the one that we're operating on. And in this case, we're only operating on row number 2. And so we added row 1 to row 2, and now this is a 0. Okay, so let's see, -2 plus +3 would be a +1. 3 plus 0 would be 3, and then 9 plus our -4 here, we get 5. Okay, so we now have this new, what we call row equivalent augmented matrix. But the nice thing is we have a 0 here. So now we have to attempt to make this 2 down here a 0, so that this leading 1 up here is the big 2 now. Okay, so what we're going to do is, you might notice, if we were to scale the first row by -2, that is, take this +1 times a -2 and add it to this 2 down here, it'd be really easy to get this to cancel. And so now you might be noticing the beauty of having a 1 up here. It makes it a lot easier to scale and multiply into the things below it, except for their opposites, so that they cancel. Okay, so what we're attempting to do now is this. We're going to say, all right, we're taking -2 times row 1, and we're going to add that on to row 3. And so row 1 doesn't change. Okay, row 2, we didn't do anything to row 2. We still have that 0 that's leading it here, 5. And then down here we'd say now we have a 0 here as well. Let's see, -2 times this positive, or -2 up here would be +4. 4 plus -5 is -1. Okay, oh, we'll go white. -2 of 3 would be -6, plus 5 is -1. And then last here we say -2 nines be -18, plus our +17 is -1. And so now here's our new row equivalent matrix where these entries are now 0. Lovely. Okay, so now we've got a leading 1 and 0s below it. Now we need a leading 1 in our second row going down this main diagonal. And you say, oh, we already have that. Awesome. So now that we have this one, what we're going to do is we're going to try to get everything below it. So that'd be this one here. To go to 0. I don't want it. I want to get rid of it. Okay. So what we'll do is we'll add row 2 to row 3. So let's see. We've got row 2 plus row 3. We'll just throw it on there. So since we're operating on row 3, the other 2 rows don't change. We got 1, -2, 3, 9, 0, 1, 3, 5. And then we added row 2 to row 3. So we say, all right, so 0 plus 0 is 0. Okay, we got 1 plus -1 is, now we have 0 here. Awesome, that's what we wanted. That 3 there, we added to -1 down here. We get 2. And then last but not least, our 5 would have been added to a -1, and we get 4. So our new row equivalent matrix. The last thing I'd like to do now is we say all non-zero rows we wanted to have a leading 1. And so I want this to lead with a 1 here. These zeros we kind of neglect, but I need this to be 1. So what we'll do is we'll just say, we'll just take half of row 3. We're allowed to scale an entire row. And I should have written that in pink, sorry. So we got 1, negative 2, 3, 9, 0, 1, 3, 0, 1, 3, 5, and we get 0, 0. Now half of 2 is 1, half of 4 is 2. And we say last but not least, we have achieved what we refer to as row echelon form. So row echelon form, or we use Gaussian elimination to get here, so Gaussian form, some call it after Carl Gauss. But anyways, this is nice because this was an augmented matrix, remember. Now, if we were to take this and rewrite the system that it corresponds to, what you see is this. You end up with 1x minus 2y's plus 3z's for our first row, and that's so totally 9, okay? Second row, we'd have just 1y plus 3z's, and that would be equal to 5. And last but not least, we'd have, hey, guess what? Z equals 2. So the nice thing about this form is that we can now use what we've referred to in the past as back substitution to substitute that z value back into this second equation here and get y plus 3 times 2 is 6, so y plus 6 is 5. So y plus 6 is 5, y must be negative 1. So we've got 2 is our z value, negative 1 for y. And even after knowing these two, we could go back up to the first equation and solve for this x value right here, okay, and get our solution. But we often want to, utilize elementary row operations to put it into row echelon form. Okay, a quick side note is this: if we were to continue, and instead of, once we made a 1 on our main diagonal, we tried to make everything below it a 0. But what if we tried also to make everything above these 1s into 0? Okay, and so if we were to do so, actually what you get is what we call reduced row echelon form, and that is anytime you end up with a situation like this, like say 1 0 0 0 1 0 0 0 1, and then you had augmented 1 2 3, and we also utilize this form because you would notice if you were to put your system back together, you'd say x is simply 1 here, y is simply 2, and z would simply be 3, and that comes about by getting all of the things on top of our leading ones to also be 0, okay? And still just using elementary row operations. So hopefully this video helps you guys out.